Okay, so this is going to be a different video. Normally, we calculate integrals by doing some rigorous maths, right? But in this video, we'll calculate this Gaussian integral from minus infinity to infinity, e to the power minus x squared dx. This is equals to root pi, right? Okay, so we are going to calculate this integral using uh, random simulation. So you will use Python to make a random simulation and we will evaluate this integral. But before we go to making the random simulation, let me tell you something that you need to understand. If, okay, so let's say we have a curve going from 0 to 1, right? And let's say this curve goes something like this. Yeah. Now, what we can do to find the area of this curve is, let's say we pick a point in between 0 and 1. So let's say this point. Now, if this curve is f of x, let's say, and the height at this point will be f of, let's say, xi, f of xi, right, or f of x1. Now, if I just say that f of x1 is the area of the curve, what I mean is, since the base is just 1, it will give us this area, right? It will give us this area. Let me highlight it, this one. This f of xi will give us this area because base is 1 and the height is xi. Though if I say this is the area of the curve, this is not correct, but it approximates the area slightly, right? Though this gives somewhat of an idea of what the area of the curve could be. Yeah. Now to make my estimate better, what I can do is I can take another random point on the curve x2, and find the height over there. Yeah. Now, if I add the its height, so that means what I'm trying to do is, if I this times 1, I can do that, right? So f of x times 1 is basically, this is 1 is base, this is height, this is the area of this big rectangle, this area. So I have the previous area as well as this area, and if I take the average of this two, this will give a slight idea of what the area of the curve would be, because the average of those area will be slightly more accurate than the single one of them, right? So what I'm going to do is, if I just take some many random points, f of x1, x2, x3, x4, if I just take so many of the random points and average them, f of x3, x4, a lot of the random points, and if I find the average of it, I'm going to get the area of the curve. Yeah. And by random points, I mean that all the points in between 0 and 1, this should have equal probability to be selected, right? All the points should have equal probability that they would be selected. And if I am able to select like a lot of the random points and find the functional values and average it, I will basically get the area under the curve. So that's what we are going to use to evaluate this integral. We will basically ask random points between 0 and 1 with the Python. We will find the functional value, we will add all of them and find the average, and then we will get the area, right? Now, if you want like rigorous mathematical proof of this fact, you can use the Riemann sum. So basically we know that the integral will be sum from n equals to 0 to basically 0 or 1 to infinity, right? And what we do is, basically, let me just write that this is f of xi times delta x, right? Let's say 1 to infinity, f of xi times delta x, where this delta x is the gap, right? And f of xi means for the ith integer, this should be I actually, from I equals to 1 to infinity. So there are infinite small gaps. Yeah, and for every, like let's say this is x, I mean if this is, let's say, in position I equals to 3, this belongs to position I equals to 4, I equals to 5, right? So this is x5, x4, x3. For all this, we find small like these areas and go on summing them, right? And delta x is just this width. And let's say if we have converted the range from 0 to 1, into n different versions, then delta x will just be 1 minus 0 by n. That means 1 by n, right? Yeah. So we see that delta x is 1 by n, so this can be taken out. So this is just 1 by n of the sum from I equals to 1 of to infinity of f of xi. Basically, this gives us the idea that if we evaluate at all the i's from 0 to 1, from all these small points, the functional values, if we sum them up and average it, we will get the area, right? This is from the Riemann sum. And this, the same thing is being happened, same thing is being occurred over here, or is happening over here. Yeah. So the random simulation will basically give us all the points, because all the points are equally likely to come in the random environment. And yeah, we will just sum them and average it and then get the area. So that's what we are going to do to find the area using simulation. So now, for that, let's first of all convert our range from 0 to 1. I mean, our the integral is from 0 to 1. So first of all, what we can do is, using the fact that this is an even function, we can change it to 2 times integral from 0 to infinity e to the power minus x square dx. Yeah. And then what we can do is, we can first of all add 1 to the x, y is equals to x plus 1, so that this goes from 1 to infinity now. And then this will be e to the power minus y minus 1 square dy. Yeah, dx is just dy. And now take the reciprocal. Let's say z is equals to 1 by y. This becomes 2 times integral from now 1 by y 1 to 0 e to the power minus 1 by z minus 1 square, and dy is just minus 1 by z square dz, right? Negative sign can be used to reflect the integral, so we get 2 times integral from 0 to 1 of e to the power minus 1 by z minus 1 square by z square dz. So we got this. So we'll evaluate this using Python simulation now. Yeah. Now I think what I will try to do is, I'll first find this integral, and after I find the answer, let's say we got the answer to this one, then we will find twice the answer, which will be root pi, and again we will find the square of this answer. This is root pi by 2, and this is root pi, and that will be just pi. And when you see that it's pi, then if we see that it's pi, then yeah, we will be sure that we have got the answer. The Python has given us the right answer, right? So let's do that. Okay, I have already written the code. I will explain what the code means. So first of all, we are importing maths and random modules, because this will allow us to use the random function and math functions. So yeah, now we'll define a function f of x such that it returns the value e to the power minus 1 by x minus 1 square, and then this is the power of e, and divided by x square, right? And what I'm trying to do is, I will take these many different numbers between 0 to 1. Yeah, so this is the number of numbers that I'm going to take between 0 and 0 to 1. Let me start with something smaller. That's just 1000. We will take 1000 different values between 0 to 1, and then find the functional values and take their average. Now first of all, the sum of all the functional values is 0. And now what I'm going to do is, so why for all the, I mean, what this will do is, this will run the code in between 1000 times. So this will just do the looping. Now for every time when this loop goes on, it will choose a random number, and it will add the functional value of that random number in the sum variable, right? So basically, if you don't know what random is, let me show it over here, Python. So let's import random, and what does random dot random does is, it will generate a random number between 0 to 1. Yeah, you can see that. So this is the task of random. I don't know. Okay. Now this will give us the number written 0 to 1, and see it's really precise. So almost all the real number space will be covered, and that gives us more accurate answer, right? Okay, and then it will sum those up and then find the average. And finally, after we have found the average of all the chosen axes, that will be our integral. So that will be our integral. And also what we will try to do is, furthermore, to make sure that we have gotten the answer, what we will do is we will then find the twice of answer, which should be root pi. Twice is equals to 2 times average, and then again we will to find pi, so this will just be root pi. So to find pi, we will find square of twice square, right? And now print the value of pi we approximate is pi. Yeah. Okay, now let's try to run this. So this will just take 1000 different axes in between 0 to 1. Let's see. Okay, so this gives us answer as 0.899. Yeah, so this basically gives us root pi by 2. Okay, the root pi by 2, it doesn't give us root pi, it gives us root pi by 2, because I'm just finding, as I have told earlier, we are just finding this integral, which is root pi by 2, right? And if you want to see how close the answer is, root pi by 2 is actually 0.886, something like that. It's slightly off, and yeah, value of pi is also slightly off. So how we can increase the precision is increase the values of n. If I make it a bit bigger, yeah, see, you see the answer is correct to 3 decimal places, and the value of pi is also 3.14158. It's correct to 2 decimal place. The third one is not correct. Okay, let's increase more, because law of large number says that at infinity it should, the choosing of numbers will be uniform, though it doesn't really choose all the real numbers in between 0 to 1, like only a certain decimal place. So there's fault in Python as well, but yeah, if it could, then law of large number says that almost every number in between 0 and 1 will be chosen. So that means it should give the exact answer. I've added 1 more 0, 2 more 0. Let's see. Okay, it's running. It takes time because this is a really big number, and to run the loop. See, 3.141. We are correct to 3 decimal place now. Yeah, you see that the more we run, the more accurate this area is, which is root pi by 2. And then like multiplying this by 2 and squaring it, we get the value of pi, which is also almost accurate. So this is how we can solve this integral using simulation. Yeah, and we can verify that because this is the value of pi. Now, yeah, so this is how we have solved the Gaussian integral. Hope you enjoyed the video and the idea. Thanks for watching. Look forward to seeing you in the upcoming videos too.